I am Makoto Kumon from Kumamoto University, Japan. I'm going to talk about drone audition as one of HARC application as a case study. As the name shows, HARC system is utilized to process the acoustic signals that are recorded from a very noisy flying drone. Here are the contents of my talk. First, I'm going to briefly introduce the drone audition, and then I'll talk about some techniques effective to record acoustic signals using a very noisy drone. I'll also explain how we utilize the acoustic information to find the position of the source or even multiple sources on the ground. What we consider in our project is to find and point out the position of sound sources on the ground from a flying drone equipped with a microphone array as shown in this photo. You can find a drone with a fine frame surrounding the body here as a microphone array and a loudspeaker on the ground, as shown here, that was utilized as a simulated sound source. So this project aims to provide the ability for the drone to say, "Hey, I found the sound sources on the ground and it locates there." I think it will be better to show the video clip first to demonstrate how it goes. This video clip was about the demo of drone audition at the simulated disaster site by the team with Professor Okuno, Professor Nakadai, and Dr. Hoshiba, and also I myself. The top left view shows a third-person view of the field, and the clip below it is a magnified one. The right-hand side shows the captured images of the system. The top shows 3D point cloud-based visualization, and the bottom two shows music power distribution at each time step on the left, and the right one shows the top view localization result. The drone took off from the launch pad and approached to the first target. The first target was the person who is going to shout from here, and you can see once he shouts, now you can see a very clear peak in the music distribution, so the system could find the rough location of the target around there, and it's going to have more observations and going to fuse all the observations and estimate the actual position of the sound source and plotting that as a blue dot here and also in the 3D point clouds as shown here. The second sound source, the person was laying inside the tube. It is a bit hard to find here, but well, here's a tube buried under the ground, and the person here is going to shout from the inside of the tube, which was really hard to detect in person, and he's going to shout. And now the system found the location of the sound source, the second sound source, which is really nice. Several challenges for drone audition as shown in this slide. The most significant difficulty is from heavy echo noise, mainly caused by rotors that locate very close to the microphone, while the target sources stay at distant locations, usually several to 10 meters or more away from the platform. So the signal to noise ratio can be negative, or in our case, it was around -15 or -20 dB, which made acoustic recognition really challenging. As a microphone array in the air can cover a rather wide area to record signals, although it might be heavily distorted. The recorded signal may contain not only the signal from the target of interest, but also various signals from multiple sound sources in the environment. And also, the microphone array can be mobile, which means it's going to move around, and its position and also attitude or orientation can be varied over time, which causes another uncertainty in the sound source localization process. Resources for signal processing and computation are also limited because drones have a limited payload to carry additional devices. Especially high-performance computation module may require rich power sources, such as large batteries, but they are usually quite heavy, and as I will show it in the following slides, the heavier the drone is, the louder the echo noise is. So it's a kind of vicious cycle. You might think that it might be possible to transmit all the recorded data to the base station on the ground control station so that the high performance computational system can be utilized to computationally heavy but high performance algorithms for processing those signals. Let me point it out that it can be another challenge. For example, if you want to transmit a 16 channel signal recorded at 16 kHz with 16 bit per channel, then it will be more than 4 megabps bandwidth, which is not that easy to realize in the real field. To some implementation tips for drone audition to deal with some challenges. The first one is about the configuration of microphones. Obviously, it is a must to place microphones close to the target and away from the noise sources. For drone audition, choices of the position for onboard microphones to be installed cannot be selected arbitrarily because of the size of the drone, and the target is always much farther than the rotors. If one wants to equip microphones sticking out from the drone, then the frame to hold microphones can extend the original drone structure, and that makes the drone much larger and heavier, which is not good even from the viewpoint of the acoustic perspective, because the rotor needs to spin faster to generate larger thrust to cancel the gravity, and that leads larger echo noise. A larger body becomes more sensitive to wind as well, and it may break the balanced stable flight characteristics, which causes unsteady echo noise pattern over time, and it makes another uncertainty to estimate the location of the sound sources. Therefore, there is a trade-off between the distanced installation of the microphones from noise to attenuate the noise effect, and the stable flight by putting all devices close to the center of the mass, which implies we have to consider some optimal solution. For simplicity, we consider the case of polygon-style 16-channel planar mic array as shown in the figure here. Considering the control effort to compensate for some bounded wind disturbance affecting the edge of the mic array, the power of the noise emitted by rotors is modeled as the index of evaluate the performance of the array. I'm not going to talk about details of that, but after the analysis, we found the rainbow-like curves in this figure, this one, that shows the estimated noise level at each microphones. And you can find that those curves are convex with respect to the size of the array. Size of the array is shown in the horizontal axis. This means there is an optimal size for the drone to have the best performance. Of course, we have to consider another constraint, such as the maximum speed of the rotors, because of the physical constraint as well. So taking this kind of constraint, then we had some analysis of the design, this version of the microphone array, and we found that this was very close to the optimal solution, although we made it by the trial and error. We considered the shape of the array itself, which means whether to place microphones uniformly and omnidirectionally around the drone, or to pack all the microphones in a small structure like a ball or sphere type shape. And those cases are shown in those two figures. So this is omnidirectional type, and this is a small compact package type. All-in-one module type array is easy to attach and easy to handle, so it's convenient to utilize it. And its structure can be rigid comparing to the larger omnidirectional type array, so it's very robust to the vibration during the drone flight. On the other hand, the distance among microphones will be limited, which may limit the performance of the array for the sound source localization. But the most significant benefit of the sphere type is that the direction of the noise and the direction of the target can be separated geometrically. So if we can do some kind of sound source separation and sound source localization, then it might be easy to distinguish a target signal based on the direction of arrival. Of course, if the target signal is coming from the direction where the noise sources exist, or the drone side, those signals coming from the drone side cannot be recognized by that kind of array. So under the situation when many sound sources exist in the environment and everything is coming from all directions simultaneously, then we need to utilize the omnidirectional structure. So it depends on the case. Let me move to the idea of how we could estimate the position of the sound source from the noisy recorded signals by using the audio drones shown so far. By analyzing acoustic signals, the direction of arrival, or azimuth and elevation angles, are available. Those angle information are two-dimensional, so additional information such as depth is necessary to determine the position of the sound source that could be represented in a three-dimensional way. To this end, we assume that the source is on the terrain that could be modeled as a flat plane. As the drone has its altimeter to measure the height from the terrain, the source position can be estimated as the point intersecting the direction of arrival of the sound source with the terrain. Giving some simple assumptions, we can have a linearized observation model for the position of the sound source on the ground, and the uncertainty by the direction of arrival and also the drone pose itself can be considered as a random variables that follow normal distributions. The example of the projected sound source positions candidates are shown on the left bottom of this figure as shown here. Blue crosses are obtained projected points for two sources that are shown by red dots here and there. You can see that there are many false detections of the sound sources, so the observation itself is very noisy and uncertain. In order to cope with such uncertainties, we introduced a Kalman filter to handle them. There might be plural or multiple targets in the environment. We introduced multiple Kalman filters to track each of them according to the detection of the new targets, and the state machine to control or manage those multiple Kalman filters is shown here. Again, this is the data that I showed in the previous slide. Blue crosses show the observed position candidates for the two sources in the field, and the drone flew along the solid black line like this. And the drone utilized to record this signal is shown in this photo that had the two-story 16-channel microphone arrays surrounding the drone. The final estimated source positions are plotted as black dots in the bottom right figure shown here. As you can see, the system successfully found the positions of those two sound sources rather accurately, and the accuracy was 2.4 meter error for the left one, that was a voice, and 1.0 meter error for the right one, that was the whistle tone. As the source position can be estimated rather accurately, we tried to separate the sound signal, as you might experience in the previous tutorials, using sound source separation mechanism of the HARC, and it can be applied to extract the target signal even for the drone audition. This video clip shows another example. Operation system is connected to the localization system, and the separated signal was also fed to the some kind of this classifier to detect what kind of the signal is coming from the source. You can find a green circle with the symbol V that represents the target was classified as a vocal signal. Of course, this is a very special case because we just trained the classifier according to the knowledge what kind of sources exist in the field. The algorithm shown in the previous slide has been extended to handle more general cases. In order to track sound sources in the field, it is not easy to know what kind of sources exist there beforehand. So we cannot train the classifier to specify the type of the sources, but that is not really required for sound source tracking. Instead, what is important for the system is to associate the given observation against the currently tracked sources. To achieve this, the similarity of the signals between the tracked target signals and the current observation is introduced. This similarity can be computed by giving some references. In our system, several reference signals are given as the basis to characterize the acoustic features, and SVM-based classifiers compute likelihoods as the distance of the signals, and the vector of the likelihood is introduced as a feature of the signal. That is shown here as the symbol S. Information such as the features of the acoustic signals. That information is fused in the data association process. We proposed a global nearest neighbor-based association method that minimizes not only the cost of the geometric distance but also incorporating the classification distance as well. I don't want to show the details of that, but if you're interested in the details, then please refer to our paper as shown here. This approach was verified and shown here. The scenario tested for the evaluation was like this. There were two sources, male and female voices, and the male voice, the first one, moved from the bottom left corner to the top right corner along the straight line, like this, and the second, the female voice, moved from the bottom right corner to the top left corner instead, like this, and two sources crossing in the middle of those paths at here, just in front of the drone. The location of the drone shown by the blue square here. Figures in this slide show the estimated source paths. The top three figures, those three, are by the proposed approach, and the bottom two are by a similar algorithm but the classification. Numbers along the paths show the IDs given by the system. So in this case, the source number 0 and source number 1 are found by the proposed approach. The number of the observations or the candidates of the positions of the sources are controlled or filtered based on the music spectrum power level to select appropriate observations. From left figures to the right figure, we control the threshold level from 20 to 19, and according to the change, the number of the observations increased, as you can see the black dots. With appropriate thresholding, that in the left and also the center figures, the proposed method succeeded to track two sources. Of course, if there are too many false positives, like in this case, even our proposed approach could not work well because the proposed method is not perfect. But even for the case, if the proposed method succeeded to follow two sources, the case if there's no classification information given to the system, the method could not follow or track two sources appropriately. For example, in this case, the male voice moving from here to there was not correctly tracked, and from here to there it could follow the track, but at the point of the intersection, then the tracker switched to the female voice, and the path estimated was like this, which is not correct. And also the female voice, the first half was okay, but it terminated estimating the location here, and wrongly the new source was generated to track here, so it found three sources in this case. I introduced drone audition as one of the applications that utilize HARC as its core. The main component of audio signal processing shown in my presentation, such as localization or separation, were all done by HARC, which was really great. And I would like to just point out here two things. The one is that a good recording equipment or system such as the microphone array specially tailored for the drone is really effective and important, and you might need to consider it for your application. The golden rule I found was to keep the microphones away from the noise sources as much as possible. Of course, it's almost obvious, but worth trying. The other is that extracted information such as the direction of arrival of the sound signals always contains some amount of uncertainty, and it should be handled according to the context, which could be important to utilize acoustic information. It would be great if my talk can be of any help for your future work of using HARC, and if you enjoyed my talk. Thank you very much for your kind attention.